Joined DRDO in 2003 as Scientist B, Dr. Goyal has made significant contributions in the field of high-power gallium arsenide and gallium nitride-based MMIC design, catering to frequency applications up to KU band. His expertise also extends to device modeling and PDK development.
Without further ado, let us welcome Dr. Umakant Goyal to deliver his talk on the basics of RF in microwave design perspective. We are eager to benefit from his wealth of knowledge and experience in this specialized field. I would like to request Professor R.S. Gupta to present a sapling to Dr. Umakant Goyal, the torchbearer for this wonderful 6-day event. Thank you, sir.
Hello. So, good morning to all of you. So, I think let me put my bar as equivalent to you only. I thought that maybe many students will also be there, but I think it is great honor for me to be here and to be part of this faculty development program, where what I think that we should get the complete flavor starting from how a technology is developed. So what I will do, because as you know, the first speaker has both advantage and disadvantage. The first thing, advantage is I can tell you everything what the other people are going to tell later on stage. Second, because this is the very first lecture or a talk where I have to make you acquainted with all terminologies and the topics which are going to be the part of this faculty development program. I am being a technical side, I am involved in the gallium nitride and gallium arsenide based device and the MIC circuit design. So let me take you through starting from where we say that a system, a big system which is consistent of so many things, but who is the heart of that system? So you won't believe the tiny devices which are actually the workforce of the whole big systems. So this will tell you the glimpse of the fabrication facility, which is actually this is the real picture of the GATEC Hyderabad, which we carry out the fabrication. So we at SSPL do the R&D, we do the R&D fabrication over here. Once the things are complete and they are matured, then they are sent for a final production unit, which is at GATEC Hyderabad. So you know this is a clean room fabrication facility where those tiny devices are fabricated. To fabricate those devices, so many things are to be taken care into account, that the room which are of the class 1, even 10 or 100. So let me tell you the brief of this. What do you mean by the class 1, 10 or 100? That in a room where if you see the number of the particles of the dust particle and particle in a cubic feet area, if you count, can you imagine that in the room this condition, if you take in a 1 cubic feet, there will be a millions number of particles. So you have to remove out all those particles from this area so that they can not rest over on the fabricated wafers. So you have to make those clean rooms where the number of particles get swept away from there and you can do the processing in a very good manner. So let us welcome to the world of this tiny devices which make the microwave devices. So this is, as everybody knows, the evolution of transistors. I am not going to tell you more about transistors, don't worry, I am also not going to tell, but let us go back and see at the time of 1947 where the first transistor was made, and now let us, when we go on moving with this decreasing of the size of the devices, with the advent of the technology development of the fabrication, how the things have miniaturized, and now today we are able to integrate so many devices in a very small area. One domain is like to miniaturize the devices, another domain is to make the devices usable at a very high frequency and very high power. So let me make it a bit clear to you. One is the technology which is the silicon technology which is going to miniaturize the devices. Where you are, how you are going to miniaturize the devices? You are simply reducing the technology node. You mean say technology node means you are trying to reduce the actual gate length of the device. So what do you mean by gate length? It is when the electrons are moving from the emitter side or the source side and to the drain. So the distance which is being between the source and drain, how fast those electrons are being swept away from that origin side, that determines the frequency of operation. So if the gate length, so there are two factors. One is if you go on reducing the length side, then also the frequency of operation increases. And the second thing, how fast. How fast means if the electric field which is generating that EMF, if that is higher, then also the frequency increases. So those two factors are governing factors to give the best performance of the devices. So there are two domains. One is the material domain where the silicon is leading the world. No doubt, it is there. It is in terms of the fabrication facilities are very matured, everything is like well settled, but that is not sufficing the requirement of various applications. So if you say the application, when we say the defense or the space applications where the requirement is in the high power and even at a very high frequency. What do you mean by high power or high frequency? So let us go in that way. For the silicon, the frequency, if it is a 1 gigahertz or 2 gigahertz or 3 gigahertz is much okay. That is the limits which are there. When we say when in the defense applications where the applications are lying in the, when we say in terms of the frequency spectrum, we will see that how we are moving from 10 gigahertz, 20 gigahertz, even at the 40 gigahertz. So the band which are actually the X band, then KU band, then the Ka band, now the applications are moving much beyond them, is like in a terahertz range. So like people are moving in the, even they are crossing the millimeter wave, they are moving to the terahertz regions. So this is what is the depiction that I want to tell you, and I think in a future lectures also you will see what is the final thing and what is the root cause of that. So let me tell you from a very perspective point of view of a system. So the very first thing which is actually the system which is SR radar, which is active electronic scan array radar. Let us go with a bit history of this. Earlier it used to be a single element radar. What does it mean? Then this means that the element which was transmitting the power to detect or to surveillance was single unit. So it was a very high power vacuum tube kind of thing. So but the disadvantage of that system is that if that one single item fails, everything goes off. So later on stage the concept came, why can't we make them item as a array of kind of thing? So if you require 1 kilowatt of power output, let's say, what do? You make an array of let's say 100 by 100 array, and each element is transmitting 1 watt power. So what it will happen? if out of those 100 by 100 array, if 1 or 2 or 10 items fail, even then you will get the output power of, let's say, not exact 1 kilowatt, but it will be like a 900 watt or something. So that is what is called the graceful degradation, and that idea came and it led to a very dramatic change in the any kind of transponder applications, whether it's a satellite communication or whether it's a radar or any kind of EW systems. So this SR radar or any kind of system, I have taken one example for you to have a little bit understanding. So each element of this will be having on the back the TR module. What do you mean by TR module? So that I will explain a later on stage also, that the communication actually happens either one way or one half way or at full way. So this is called like a, in a single system you are having a duplex kind of system where you are having the transmitting and the receiving at the same time, but there is some interval with a pulse. So each element of the antenna, which is at this side here, which is visible in the patch antenna, is being fed by the TR module. So the TR module is having what? It is having the transmitter side, obviously it will have the transmitter power amplifier, and the receiver side, from the signal which is being received from the antenna, it will receive through the LNA, and this whole mechanism will be switched by the air switch. So this is a very simple mechanism by which we can understand a TR module. Although it is having so many, I will tell you later on stage how the complete TR module look like and what are the parts which are the basic building block of a TR module. So again you see the all three parts like a power amplifier, a low noise amplifier or a switch, the base building block of all those components, active components, is the transistor, which is the tiny transistor in the size of micron size. And these transistors, these FET or devices we call like a HAMP nowadays, which are actually the high electron mobility transistors. I will tell you how the MOSFET has come to a long journey to the HAMP and how it is giving the better performance in terms of mobility as well as the frequency of operation. So these are the transistors which, if you see here, this is a HAMP device, GaN-HAMP device, gallium nitride base, which is two-finger device. Let me tell you a few terms which I will repeatedly tell you, and let us make it a bit interactive session, because at the end I will have a quiz. You have to give the answer of that, so you have to be a bit interactive. Okay, so this is a two-finger device, which is, what do you mean by two-finger of device? Let me explain this, because I think this. So
इसमें more sense.
the laser will not be detected by the
Oh.
sensor. Yes.
Okay.
You can
So
switch on the slides.
So this is okay, I can run out the mouse.
Yes.
So this is the, if you see here, this is the source, the first one, and in between there is a drain and then source. So it's a very normal, any device when we say emitter and then the collector, in between there is a base. So similar way, this is a source, drain, and in between there is a gate. So very thin line which is visible to you is one gate. Okay, so how many gates are there? There are two gates. See, below this there is another gate. So this is where one gate we say it's a two-finger device. When we say number of gates are two. So why the gate? So if you see the vertical distance between these two, like between this to this is called the gate length. So the electrons are going from source to drain side. So that length I was saying. If you go on reducing this length, then the frequency of operation will go on increasing. So that is the very first thing. That's how the technology is developed as a node wise. When we say, because you have heard like in CMOS you say now 180 nanometer technology has come, 65 nanometer technology has come, or nowadays we can say in the R&D even like 10 nanometer or 8 nanometer technology has come. So what does it mean actually, the 8 nanometer? It is the distance between the source and the drain where the gate is lying. So to write or to fabricate those gate at such a level like at a nanometer is the art, or you can say the techniques. So to writing those earlier days with the, like when we say the micron kind of gate, which is where the gate length one is in the range of micron, they could have been written by the photolithography. Very simple mechanism where you have the mask and you do the UV light, you illuminate it, and wherever you want to be printed, they will have a dark mask or the bright field mask depending on the photoresist material, and then it will print. But there is a limitation on that photolithography process. What is that limitation? Because you know that the UV light has its own wavelength, which is passing through those tiny slits, and they have the wavelength which actually limit in the range of 700 nanometer or not beyond that 500 nanometer. So we could have written 0.5 micron, means 500 nanometer till you can write with the photolithography process, but not beyond than that. So that is a very critical path where the technology stops actually. So there the new techniques came into writing, like where you directly write the gate by a direct E-beam process. It is not now photolithography, it is a direct E-beam lithography, where you simply bombard the electrons and you simply write on that wherever you want to write. Now you can say what is the problem in that? Because to write each and every electron on that space surface area will take so much of time. So you do whole processing using photolithography, but to write those tiny kind of like structures where it is only the gate, that you write with the process of E-beam lithography. So that thing should be very clear to you why technology is like taking a mix and match kind of. This technique is called mix and match for lithography, where most of the content you write through the photolithography, but only the part of that which is the gate, which is very tiny, or you can say the feature size of less than 500 nanometer are written by the E-beam lithography. So this is what is the basic overview, and now you can see that. So I am taking you through that path, and then I will tell you the basics of the design, and then we will see the perspective in the device modeling perspective also. Okay, so this is what is you are having complete. This is a complete TR module where you have a receiver path where the LNA is there, the filter is there, and the mixer and anode is there. And then in the receiver path, if you see, you have the same action of that arrow, and then you have a filter and PA. So if you see, the main focus is on three devices. One is the low noise amplifier, which is at the receiver side, power amplifier at the transmitter side, and the switching of both the paths is through the switch. Let me tell you one more thing earlier, because this switch is actually the, what we say, it does not know what is coming to that. And in a war scenario or in a normal scenario, when you do not know what can come to you, someone can feed a very high power to you and it can destroy the switch. That is what. So the switch has to be made so that it can handle much more power what it is rated. So normally what we do, we use the circulator or a very high power sustaining switches in that. But you know, like this is what is the way how technology progress. So earlier days the switches were made of a ferrite or any like big, which was big in the size, though they can handle big power. But with the advent of the gallium nitride technology, where the gallium nitride device itself has a very high power capability, so the transistor of those gallium nitride devices can directly be used to make the switch. And you won't believe the size of those. I will show you. You are seeing this complete TR module, which is of the size of few centimeter by few centimeter. And now this complete TR module with a high power of 10 watt power output and the low noise amplifier and the complete switch have been reduced now in a single 4 mm by 5 mm chip size which have been designed and it has been validated, and that also up to KU band. We have demonstrated it, and I will show you those chips. So that is what the beauty of a technological advancement. How you can do the design in a miniaturized size with a very high power capability and a very high frequency. So this is the glimpse of that. So this is how I want to say that at SSPL or at in any. So I am not going from my institute wise. I am taking you from any technology development which is happening, whether you call it RFIC or you call it MMIC or you call it IC, generalized IC, where you have to start from a gallium nitride or any material. So see, this is the gimmicks they are moving: silicon, gallium arsenide or gallium nitride. They are the material. Silicon is very good in terms of, because it is easily abundant, easily available. Technology is very well advanced. Fabrication is very cheaper. But there are limitations in terms of frequency and power. Then came the development of the gallium arsenide material, where the processing was a bit difficult, but through the time it was established. But it was not having that much of power capability because it was having. So let me tell you, what is the thing which is governing the power or the temperature handling? It is, what is the thing which is governing? Can someone tell? The band gap of the material. The band gap is actually the very high in gallium nitride, which is 3.4. So obviously you will require much energy to break those bonds. So that is what it gives a very high temperature capacity or a very high power handling. And that makes it a very good material for today's requirement. But obviously nothing comes like a free lunch in this world. Gallium nitride cannot be grown or it cannot be fabricated directly on its own substrate. It is very difficult. And till now, after I think more than 18 or 20 years have been in the world, but no one has grown the gallium nitride on its native substrate. It is very cumbersome and it's not possible. No, I will not say it's not possible, but it is very tedious process. So later on it was thought, can't we go for a different substrate? So people explored the silicon. Obviously, everybody would like to go on a available kind of thing, silicon. Then they went for the silicon carbide and then the sapphire. So these three elements were explored, that which will be the best suited. Again, they were trade-off, that the silicon carbide being the very expensive material, but it gives the best performance in terms of thermal conductivity. So let me explain that. But बोलते हैं कि can I speak in Hindi in a mix? Hindi English? Okay. So चीज तो हमने अच्छी बना ली, बहुत बढ़िया बना लिया, पावर दे सकती है, it can generate so much of power. But you know that to generate that much of power, it will generate so much heat also. Because nothing is coming like, see how the RF power is generated at the cost of the DC power.
Sir,
Amplifier is, yeah.
Sir, you are telling that gallium nitride is having the mode band gap than the silicon. So if it is having the mode band gap, so how it will be fast than silicon?
Exactly. So okay, let us now go with more deeper in the device. First of all, the MESFET. MESFET is simply a semiconductor, and over top of that you are making the metal semiconductor junction which is short. So there obviously the electrons will be coming into the semiconductor side. But later on when someone told that the electrons which are coming from the ionized donors, they are creating the problem in the motion, which is we say that the scattering kind of phenomena. Then they came into the idea of why can't we make the electrons which are actually taking part in the action of the current, they are actually isolated and they are being away from those scattering elements. So what was the concept of the heterostructure where it comes? That you use two different band gap material And if you will mix them, and then if you will go to the basic physics theory, that the electrons from the higher valence side, they will fall and they will make a bare kind of structure at the interface. So it is not like that the electrons have to be taken out by imposing the energy and then they will come out. No. It is like two different band gap materials are there. So here in this case, we have the gallium nitride and the aluminum gallium nitride. So you can make two different band gap structure by making the impurity of any, nowadays indium gallium arsenide also there, aluminum nitride is there. So two different band gap material, you make them the junction, and at that junction structure, those electrons falls and they are trapped in a two-dimensional well kind of structure, which is actually called two-dimensional electron gas. So you should get those terminologies, 2DEG, and that is what is the phenomena of a hemmed structure, where you take out the electron, put them like हम कहते हैं वहां से लाके and you drop them in a bare kind of structure which is two-dimensional. Now the electron will not go in a 3D mode; they will be in a sheet carrier kind of sheet carrier, two-dimensional structure, and there they can freely move, and it really enhances the mobility of those transistors. The question for your question, like electrons are already there, they are there. You are not imposing energy to take out the electron. You are taking out the energy to, now if I am saying that so much heat is being generated, so much power is being generated out of those devices, even then my structure is not being known. That is where the higher band gap phenomenon is coming. So these devices plays a big role in generating a very high power at such a high frequency. Now you will say at what frequency. So if you see the gate length, we started from a 1 micron of the gate length in a gallium nitride, then it moved to the 0.5 micron, the simple Moore's law that we say. But here, let me tell you, in gallium nitride of these technologies, no, we do not follow those Moore's law, because we cannot go like every time the half of the size, but up to some level we go like this. So 1 micron, then 0.5 micron, then 250 nanometer, then we have gone to 150 nanometer, and now it is going to the 100 nanometer. So that is how the technology node is moving. So if you see here, this is the full wafer, and the gallium nitride wafer. So let us concentrate on that way. There were three materials: silicon, sapphire, and silicon carbide. Silicon carbide wafer is totally transparent. If you see here, this is the wafer on which the complete apple layer is grown first. Like apple layer means you will grow the gallium nitride on top of that. So that is also one process which is actually the material. That one full lecture will be there for you for how those nanometer layers they are grown, and the material is made to work as like a device. So you generate those active areas in that. Okay. Once that material is grown, then the full processing is done, and you have those devices fabrication, and then you cut out them. First of all, you do the characterization on wafer. What do you mean by on wafer characterization? That the full wafer is there, but you have the probes, tiny probes, which are actually going up to those 100 microns of the pad size, and then you characterize them in terms of DC, IV, you characterize in terms of S parameter, and then you characterize in terms of the pulse IV and the load full power. So these all terminology you will see one by one step how these things are done, and they are the workhorse of any technology development. And then you cut out those devices. So this is the finger on which you see this is the device, which is the power device, and which is used to design a power amplifier or load amplifier, any kind of this. Okay. So this is, I was not about to put this slide, but let me give you the whole SSPL, what you will listen, what you will see the complete MMIC technology development in a single nutshell. So if you see here, so this is what, so see, any technology development will have its own application. So our application for any technology is the, you say in terms, I have already told the SR radar or the electronic warfare applications where you require a very wideband application. So any development or any novel idea comes from when you really think where it is needed. I will tell you 2-3 examples where the innovation has come from only the requirement. Until unless you will really feel why I am doing this, why it is required. If you will not give the emphasis on that, you will never come up with an idea. So, EW systems where what happens, you have your own system, someone else can do the jamming of you. So jamming is actually a big thing where you require a very wideband kind of application where you will also try to jam someone else. That is what is called the counter reason. You, पता है दुनिया में you are developing something, but सामने वाला कम नहीं है. He is also developing something. So they will also develop in the same band or another band, but you have to counter them. So for all those applications, you require the wideband kind of amplifiers where you can jam them. You can pump in so much energy so that you can. That's what I told you. You pump so much energy in the complete band, and they are jammed. Like their system will go on. So that is what is the application that comes. And obviously for the satellite also, all frequency band satellite which have the TR communication, where the transmitter and the receiver, you will require all those power amplifier, load amplifier and the switches. So what I was saying, this is the very first one, which is the silicon carbide wafer. So let us go with the step. First of all, you will require a wafer, which is a substrate. Okay, so this is a bare wafer. So right now it is the silicon carbide or silicon which are in the worldwide used. So this is the first silicon carbide wafer which are actually developed. This itself is a big dimension where the fabric, the material technology is done. The second one is the epi layer, which is the material. This is the epichrome. And third one comes the device technology and the design and the modeling and the characterization. And from that you see the last list, which is actually the what I was saying is this one. So you see here, this is the complete front end chip, or we say the TR chip, which is having power amplifier, low noise amplifier and the switch in a single 4 mm by 5 mm size. So how this is all possible? It is possible with the use of those technologies, and how these designs are done you will see in the next afternoon section. We have like it is planned how to design a power amplifier or a low noise amplifier using those tools, using the load pull techniques, how it is give you the insight that starting from the device structure, device data, how we can go up to the power amplifier design. So that will be covered in the second lecture. So this is what is in nutshell how we are starting from a device and then leading to the technology. So this is in wideband as well as in the narrow band, design is as critical as it is there. But you have to know the basic concept how to go about the design. So for that, so this is what is the overview, because I think I was told that in the first 5-10 minutes I have to tell you the brief, and then we will move on to the final to the basic lecture. So this is what any technology is made up of 4 parts. I have repeatedly I am telling you because that will give you the insight, and you can be conversant with the talk that in what field he is going to tell. So the very first thing is the material development. Then it comes the process technology, where we are saying the photolithography, where we are processing the thing. Then it comes the RF design and the modeling. And the final one is the measurement and the packaging. So that is how the complete cycle goes on to develop any technology. So see, this is what, if you see this picture and you become conversant with that. So this is the most difficult part of the any processing part. So if you see, this is the source, and this is the SAM image of that device. This tiny gate which is lying here, so this is the gate. And nowadays it is written with the metal is directly right on the substrate with the help of e-beam machine. And this is the drain and this is the gate source. So you are having two gates here. And now you can see here is the multi-finger devices, which is 3 mm device of the size, which is generating 15 watt of power. in a single device. So this is what have been fabricated, and they are the real working things which you can. And now this is the full journey starting from the wafer. You see the wafer. Then in a wafer you have. So let me tell you this story also. How the processing is done. So what you do, you design some circuit. Okay, if I'm so let's say there are so many designers with me, and we give them like, okay, you design the power amplifier, you design LNA, switch, any kind of device and all, and then you make a tile of that. What do you mean by a tile? Tile is consisting of all the circuits, and they are packed in such a manner that later on stage when you try to dice them, they dice properly. Okay, so it is like a art kind of thing. And the top level people has to do this. Like they will plan the tile. Okay, so the size of the circuits will be defined by the tile, and those tiles will be repeated on a wafer. So that later on stage, if you see the one wafer is consisting of the order of, let's say, around 60 to 70 tiles in a wafer, and each tile is consisting around 10 to 12 circuits. So that's how you have more than around 600 or 700 circuits in a wafer, complete 4-inch wafer. So this is the wafer. In the wafer you have a die, and this die is diced. So this is the device, and this device is then packaged, and then after packaging you do the circuit design. So let me tell you again here two concepts. This concept is called MIC, and another concept which is called MMIC. So what is the difference between these two concepts? The very first one concept is MIC, means you take out the device, dies, and then do all the juggling of the designing, which is the PCB design. Or you use the assembly components like resistor, inductor, capacitors, you do separately. It is like some kind of, you have heard, I have one slide on this, like earlier days when we were in the starting, we take first year, we do the breadboard design. So you have all those components separately, like the device is separate, the resistor, capacitor, leaded one, they are there, and then you make the jumble of the wire on that, and then you do the design. That is the one way of the starting, crude way of the design. Then later on stage, what you did, you replaced those jumbled wires with the help of tracks. You made a PCB where you replaced those jumbled wires for the connections with the help of trace. And then you place the component on that resistor and capacitor. They are the assembly component. So this is called the MIC design. This is the one way of approach. But now you will tell why MMIC and why MIC. MIC is a faster way of giving the things. That jaldi se mere ko koi device de de, ready-made available ho, I do the design of that, and then I do the PCB. But this is not an iterative process. You cannot do the volume production with that. In MMIC, what you do, you design the complete thing in a single go. All resistor, capacitor, inductor, all the device, they are fabricated in a single go. And then you will have the complete circuit which I have shown. So to have the MMIC design, how the things are done, we will go through, I will take you through the complete, how the design is done, like basic of that. So this is what our issue is, where we are doing the fabrication and complete designing. So this was the starting lecture was for the inaugural kind of thing. So now let us start with the main topic, which is like for me, like how we can go with the basic of the RF and the design modeling. This is a design perspective of, you can say, the modeling perspective. So this is the outline of my talk, like introduction to the RF technology. Then obviously the need, where the spectrum, where it is being used, all the design. Then the basic of this RF communication system, where I told like duplex or a simplex system. Then there are many facts of an RF designer that you will see, and then high frequency effects are there, that based on the Maxwell equation, how, see, let me tell you, when I was in BTech, at that time there was a course electromagnetic theory. I was having discussion with Gupta sir that everybody used to be run away from the subject. Everybody says this subject, this is not my part. I will not do anything in this. And it is Almighty that now landed up in that same line. So it is like, it is not like the way we perceive the things in the very first go or any subject. When you go in a deeper and deeper into that, then you will see the realize that how beneficiary or how good those things are there. So I will take you through those journeys, and then the practical approach of that, how we can understand that high frequency facts, how they come into picture, and then few facts that when someone do the design, why all these things comes into picture, that everybody says why 50O, or the what is transmission line, and what is S parameter, and what is the Smith chart, because these are the basics of the RF design. You cannot run away without them. They are the part of the design, and you have to understand that if you will really try to understand how the design is done, you have to understand them from a very basic concept. So, and then I will tell you the MIC and MIC technology. Then another approach, like how the devices are being modeled to use for a designer, and they are being developed in a process development kit, which is PDK, which is actually the main thing which is to be used by a designer. So anyone who is using any kind of library, they will be using the PDKs. So how those translation from a physical device to the model, that will come. So you know what is RF? It is very simple. Like when we say in a very common way that starting from our 3 kHz to 300 GHz is a very wide spectrum. When we say we are doing the design in this RF mode. Later on, so here what happens that it is not like the properties of those things are not as we see in form of DC or a very low frequency of alternating current. Here actually the frequencies are in the starting in the range of gigahertz, where things are moving so fast, they are not the way we perceive in a normal mode. What are those things? That, let me tell you one thing, can you measure voltage or current at such a high frequency? Can you do those things? When we used to do 2-port parameter kind of measurement, what we do? We make one port either open or we make one port short. And then we carry out the measurement like how much current is flowing. We say that Z11 or Y11. But here in RF, you can never achieve an ideal open or ideal short. Why? Do you know this thing? Like, what is the reason behind it? Because, and that is also, like, see, this thing also will come when you will see the Maxwell equation, like how, when you say, I am holding this thing, which is open, and this thing is carrying current, let's say, okay, this back side. So, do you think this is open in a RF, in a very high frequency mode? No. Even in the air, when I say I am holding 2 wires and it is carrying current, how the current is flowing through this? The air itself is acting as like a medium. And that was actually the revolution to the wireless world. Earlier people used to say, no, this will not happen. If I am making it open, then no current will flow. But in very high frequency domain, actually the current flows, and Maxwell gave it as a proper name, which is called the displacement current, and which is actually happening to the available dielectric media, which make the dipole in that, and that gives the current. And that itself gave the idea that we can have a wireless communication. So, and similarly, same thing if you see. So this is what, same thing the current. If you say current which is flowing through the wire, if it is a DC, then the current is flowing through complete wire. Do you know that? And if you say the AC current, that also in a complete mode, but when you go for a very high frequency, like in a gigahertz range, then the current on a conductor does not travel throughout the conductor. The electrons are actually being swept away on the surface of the conductor complete, and below that, if you do not have anything also, then the current will flow. That is where the concept of come like hollow conductor. Like if we have only the layer of that conductor, and if it is hollow, then also the current will flow. That is where comes concept of the skin dance. That the electrons, that the current level will go exponentially down from the top surface to the towards the center, and it will decay down at a e की power of that level. So there is no use of the conductor in between them. That's where comes the concept of the coaxial line. So that is where the concept of the microwave are coming into picture, and they are really giving to the need of those design where we can harness those concept. So this is what 3 to 300 gigahertz. But later on stage, this also again divided into so many bands. Like someone told, like RF domain is divided into HF, then VLF, then UHF, EHF. So that way, so every country has divided those bands as per their standards. But normally, as like IEEE standards, it is divided into like starting from L, then L band, then S band, then C band, X band, then KU, then K, then K, which is like 1 to 2, 2 to 4, 4 to 8, 8 to 12, then 12 to 18, and 18 to 26, and 26 to 49. So that is how the band structure goes, and it gives us a demand and supply kind of thing. You know the spectrum nowadays, everybody try to grab the spectrum, and even in the commercial also, as well as in the defense and space aviation. Because every country try to be capturing those bands as soon as possible and to do the design on that. So this is the complete EM spectrum that you know, like this starting from very low frequency to very high frequency, even extreme high frequency. So our domain is like, again it is divided like microwave and millimeter wave. So millimeter wave, why it is called millimeter wave? Can someone tell me why the millimeter wave is called millimeter wave? Because the wavelength is comes in the range of millimeter. It comes starting from 3 gigahertz to like 30 gigahertz. So beyond 30 gigahertz, it becomes millimeter.
30 gigahertz to 300 gigahertz.
30 gigahertz to 300. So 3 to 30 it becomes microwave, and 30 to 300. So where this becomes millimeter. So now someone can tell why microwave is called microwave? You think this
So wavelength is in
was the wavelength in microwave?
the microwave range.
No. It is in centimeters. Okay, you think of this question. Okay, so this is where the communication system comes into picture. I was telling that earlier days now that simplex system was developed. Then later on the half duplex system was done. And this is what we require, like the full duplex type of thing, where you will be having the complete transmit and receive at both ends. So you will have the TR kind of thing in both ends. You are having the TR at this end also, and you are having the TR at the other end. So these all are the basic building block of a complete TR system, which is like you are having the RFIC, and you are having the LO, and then you are having the matching network and the filter and the antenna. So these all are making the complete system of a TR. These are the few hiccups in the RF domain. Everybody tries to avoid that. What is phase noise? Because no one wants that phase noise. So, but it is a part of the designing. When we do any design like any whether it's a power amplifier or any system, there the phase noise comes into picture. So we want very clean signal. We say I am transmitting my signal, let's say 1 gigahertz. So I want my signal very clean, but in real domain, in a normal condition, it is not there. You have a phase noise of in a wider node, you always receive some noise. And that when we do the demodulation or when we translate at a lower frequency, those phase noise comes into our desired domain, which is actually hindering. So if you see here, this is where you require the domain like a green one, but that is coming into picture with the interfacing noise. So always these are like hiccups, like these will tell you how we should have a minimal phase noise, you should have a better insertion loss or better return loss, which will define the design of any system. So how you define those? Let us go. So this is what I want to say from the starting. First of all, that microwave, it looks like a black magic for so many. And people say also like this, that अबे कुछ समझ नहीं आता, पता नहीं क्या हो रहा है. And in the starting, really it happens. So it is there, but we should not go with the words that it's a black magic. Things are there, they are well proven, and when you really apply the theory and you link it with the practical, you will get what it is. So, and again, second thing, RF microwave design is not a white collar job. Let me tell you, you have to make your hand dirty. Means it is not only like doing the design on a computer and then your things are done. You have to do the design, you have to do the fabrication, and then you have to do the characterization, and then you will come to know really that what, because there will be so much variation from your simulation to the design measurement. So many times, because this is what we also see in day-to-day life, that the simulation is saying something, and then when it is giving very good result, everything is matching, and when you do the fabrication, and then you end up with the okay, this is not happening, because this may be due to so many reasons. It's not the fault of a designer. See the raw material, the substrate, the quality of the substrate. Second is the processing. When you are doing the processing, obviously so many parameters can vary. In one MMIC fabrication run, in any IC fabrication run, requires more than hundreds of steps, which are each and every step is having a probability of failure. So you cannot say that the design has been done wrong. It may be at any point of time, but that is where comes the expertise or the leading, that who is the winner at that. So the process has to be very well established for any technical role. So this all the again it comes the which are other factors, the parasitic kind of thing. Now let me tell you, in this high frequency domain, even a small line where what you print is act as like a circuit. That you have to understand. Because the transmission lines which are actually passing the signal. See, earlier days when we say the wires are there, they are okay, we are working with them at low hertz level, no problem. But when you go at a high frequency, those wires will act as like an inductor. When you print them to minimize those inductors, then even when you go with at a gigahertz range, those printed lines also will act as like a transmission line which have its own impedance. And you know that impedance plays a big role in the design. When we will go step by step. So it goes like this. All the sub-block of any system, they are actually connected to each other. When I say that one component will be added to the another component, then how I connect those two components? So it is like a amalgamation of like when we say the married life example आता है, that husband and a wife is a very practical example. When two things are far away, for them it's a very goody picture. Everything is good. Life is so good before 1 year or even 1 year of the marriage life. When you go and meet and the real things start, there we say life में लोचा है. So it is what is the impedance which are coming into picture, and then the reflections are happening. Now, let me tell you the analogy of this. It is really that way that whenever any two systems which are actually, everybody has its own aura, you know, every individual has its own, what I call is like its own impedance. So this is having, let's say 100 ohm impedance, this is having 25 ohm impedance. Till that they are far away, everything is good. He is saying from so far, अच्छा है, बहुत अच्छा है. But when these two impedances are coming and they are coming in a very near region, then that reflections start. So what to do to minimize that?
Matching.
घर वाले बहुत कोशिश करते हैं, सारे गुण लाने की कोशिश करते हैं, लेकिन फिर भी नहीं मिलता. So now it comes the matching, and that is really a designer job. How to do the matching? You will have different impedances of different networks, and then you have to match them, and then you will say चीज अभी भी वही है. अभी देखना इसमें अभी भी ये 25 ओम पर है, 25 ओम पर, और ये अभी भी 100 ओम पर है. I will put something with the interaction of these two. I will make some network. जब मैं यहां से देखूंगा उसके साथ ये आइटम है, ये entity A, and with this network, if I see from here, I will say that this is 100 because I am 100. And if that other side will look into from that side, then with this 100 and this network, it will look like this is 20. And that is what is called the impedance transformation. Balance. But in real life क्या होता है? You have husband, you have wife. So that network जो हम create करते हैं वो क्या होता है? Baby. Everything is done with the transformation. बस उसके उसी एंगल से देखते हैं, and तभी लाइफ आगे चलती है. So this is what is a simple analogy. If you will try to understand, if you will apply this thing to in your daily life, when you do the designing, it is all nothing. It is all impedance transformation. Think of everything in terms of भाई तेरा लेवल क्या है, impedance का लेवल at any point, जहाँ पर भी मुझे डिजाइन करना है, at that moment what is my impedance and what transformation I have to make, what impedance level I have to present. You take any example of a power amplifier design or a low noise amplifier or any antenna design, everywhere there will be a matching. And for that, and this matching actually will give you the best optimal transmission of the power or signal, where the reflections becomes minimized. So that is where you want, what you want? You want to minimize the reflections, so that whatever I am trying to send and it goes away from that side. Okay? So, but to do those, to understand those things, you have to understand why this S parameters, Smith charts, they are the real things where by using those, understanding those concepts, only you can do the matching. Okay? So that's what, like, my job is to make you understand little bit. I don't know how much I can impart you to have, but at least you should get, I will be happy if you can get 10% or 15%, so that you won't believe that later on talks, they will be like taking you as like a understanding that you know what is S parameter, what is Smith chart, what is transmission line, and what is impedance, and what is matching.
Sir, power can be transferred from one device to another if the two devices are isolated.
If two devices are
Isolated,
yeah,
power
then
can be transferred. So,
yeah.
so there is no problem of this small thing. झगड़ा नहीं होगा किसी के साथ.
No, but
दो आदमी isolated.
they are transferred. See, that is where the whole theory goes. And let me tell you the one point of that, why 50 ohm. Let me tell you that also. See, from where I am sitting, I see everything as like a system. For me, the radar is a system. Then I do the disintegration of that. I go below that, I want DR module. DR module, which is consisting of 7 to 8 items, which are actually combination. They are obviously architecture have been made. It is like idea from the starting. But those components, they are placed with each other. When you keep two items with each other, you have to define some impedance level where they are matched. If this matching will not be there of the impedance, that internal reflections will go on, and the power which you want to transfer from one port to another port, which kill in that reflection zone itself. it will be transferred, no doubt. But the power which you want to transfer, let's say 1 watt from this to this, like see, for you the device is nothing but a source also. A signal generator also source, which is generating some power and which is going to the power amplifier, which is being driven from the source. But that 1 watt power will not go to the amplifier if the signal generator will not have its own impedance of 50. Okay, now push. I'm not going to that point right now. Everywhere you say, दुनिया में सब चीज अब क्या हो गया 50 ohm 50 ohm 50 ohm 50. See, this is how the standard has been made. Otherwise क्या होता, हर बंदा हर जगह पर अपने अपने impedance, ऐसा नहीं है कि 50 ohm impedance में यदि वो नहीं है तो उसका काम नहीं हो रहा है. It is there, it will work, but somewhere it has to be made as a standard, and for that also the reason will be there. I will explain why this 50 ohm has been taken as a standard in the microwave industry. Do you know अपने घरों में जो केबल आती है, अब तो खैर आजकल बंद हो गया, आजकल सब OTT प्लेटफॉर्म आ गया. घरों में केबल चल रही थी तो वायर आता था, है ना, वो लगाते थे अपने उसमें केबल सेट टॉप बॉक्स में,
वो 75 ohms,
तो वो 75 में काम कर रहा है. And you know that पावर की जो केबल्स होती हैं, those power cables, they are not at 50 ohm, they are having more than 100 ohm. And if you say the free space right now where we are sitting, if you want to measure the impedance over here, this is also not 50 ohm, this is 125 377. So it is not like that the impedance in the real life is 50 ohm, but let me tell you right now here itself that the cable वाला क्या चाहता है, केबल वाला चाहता है मैं एक घर से दूसरे घर में, दूसरे घर से तीसरे घर में, जहां मैं जा रहा हूं, मेरा सिग्नल मैंने एक जगह घर से भेजा तो मैं जितना लंबा दूर तक मेरा ये वायर सिग्नल को लेके जा सके विदाउट यूजिंग द रिपीटर. सो ही वांट्स मिनिमम अटेन्यूएशन. उसको मतलब नहीं है कि पावर कितना वो हो जाएगा नहीं होगा, वो चाहता है मेरी पावर तो बहुत कम है, कोई दिक्कत नहीं है, घर में बस वो झगड़ा भी आ जाएगा, मेरा काम चल जाएगा, है ना. ही वांट्स दैट. सी द इकोनॉमिक्स. He wants that without using repeater, I can do the less attenuation. And you know that the coaxial cables and those RF cables and those frequency where they transmit, the minimum attenuation that occurs at those 77. And when we say the power transmission line, which are actually when the power handling comes into picture, that the power handling comes at 30 to 35, the maximum power handling of those coaxial. अब यहाँ आता है role of a the big people which are sitting on the top. They say that मुझे तो दोनों चीज चाहिए. हम everybody wants कि मुझे ये भी चाहिए और मुझे ये भी चाहिए. So they say I should have a better power handling and at the same time I should have the power the lowest attenuation. So to take that amalgamation of both the phenomena, then later on the people decided that we should have the impedance in somewhere of that between, which is they assume like a standard number 50. So that's how the so it's not a magic number कि वो ऐसे हवा में आ गया. There's the physics and this everything is there. So and that also gives a confidence to the designer that okay, he will disintegrate the top level people will decide and they will disintegrate the whole modules in a 50 ohm environment. So everybody will do the design in a 50 ohm environment and they will simply disintegrate to make the system. So that's how, like if it gives you answer to your question, I think that that's how everybody want to make the system design in 50 ohm. So now let us come to the basic concept. Why these things, and although I have already told you that at those frequencies, small transmission line also becomes important. Why this is there? So to understand this phenomena, okay. So this is what like at those frequencies we cannot measure the voltages and current at a because they are you cannot get the complete open or you cannot get the ideal short. So that's why in this frequency domain you measure the powers. Okay, so you measure at the ports the power and the reflected power and the incident powers. So this is because this has a spatial behavior. here it is not only the time domain, it is a spatial means as you go on in the X domain, there are also the signal varies. So to take into account this, I have already explained you like how the current, this is the RF perspective. Like in a DC domain, you have a complete current which is flowing, but when we say in the RF domain, the current will go down from the top and it will go down in a very faster manner, so only the current will flow in the surface here. So here the concept comes as, because you cannot, you will use a very minimal kind of a conductor which is at the top. So this is what I was saying, that the design approach is like either you have an MIC approach which is based on a discrete component, or another approach is like in a MMIC. So in MMIC also, or in MIC you use obviously the transmission line as a connection, and then you use either use the waveguide component. So and what are the governing parameter? That also I told. One is the frequency of operation, and another one comes the power handling of the circuit. And obviously you will require the high Q of that circuit. So again, this is the things everybody go away with them. That see, any design which will be done, either whether it's a simple electrical simulation or any microwave simulation, obviously on the back end of that, some equations will be solved. So for a normal design where we say the KCL and the KVL applied like on each node, here in microwave domain, you define the Maxwell equation. So everybody like which are mainly based on the Gauss or the Faraday laws. So I will simply say these all four equations which are actually solved at T. So what it is done in any simulation? What is done, like each surface which you want to simulate, which is divided into very small tiny parts, where what is assumed, like the boundary of those each element is conditions are seen. It is like when we learn that integration by parts. How you do the integration by parts? You define very small area where you can say dx is very small, where things are same, and then you go incrementally increase. So that's how the whole simulation theory goes. That you define one boundary where you say that the boundary conditions of this x equal to 0 and delta x and both are same, and then you solve those equations at those boundaries, and then you go on and adding those equations. So that's how those four equations are used, and these are in the frequency domain, which are actually used in the main simulation tool. So this is not to be like go in a bit of detail, because that is what is job of any developer which are used like softwares like ADS or Microwave Office, which are actually running the background simulations. Okay, so this is what actually we should understand. Part of that I have already told you, and part of things we will go. So first thing, because everybody will be going to design in 50 ohm, so that is where the concept of 50 ohm. Why everybody is going for 50 ohm. So one is having the power handling, another one is having the attenuation, and mean of that is at 50 ohm. So everybody, so it was decided that we should use the design, each component design at 50 ohm. So obviously this will, so the top people, what he will simply say, you design this system in 50 ohm, you design this. So every time he will not say that मुझे 50 ohm में चाहिए. What he will say, you design this system, you design this system. It is understood that he has to design in 50 ohm environment. Okay, so that he can simply club all those designs and then make a system. So later on comes the concept of the transmission line. So you know the transmission line, it can be made in a very different format. The very simple format is the coaxial transmission line, where we are saying the central you are having a conductor and the outer side is giving us a ground. So from one center conductor from where the current is flowing to that, the electric field line will start from the center and it will terminate to the outside, which is the ground, and which will make the coaxial line, which are normally widely used when we do the transmission in an open environment. Okay, in a long. But then each transmission line has its own characteristic impedance. This should be understood. and it depends on its three physical parameters like what dielectric between the conductor and the ground is being used, which normally we say the Teflon or an air or a different dielectric they are used. Then we say that what is the width or a length of the transmission line, which is the physical parameter. So when we design any transmission line, we should think in two terms. First is the physical parameter and another one is the material parameter. Material is the substrate. The substrate is the dielectric constant of that substrate. And the second thing is the physical kind of thing, which is actually the width or the length of the transmission. Or we say here the length of the coaxial. So normally, again the same concept comes that if you see this is the another look of this, which is the microstrip line, and this line it becomes very famous in the microwave world. Why? Because this is very much easy to fabricate. Because here what happens? You have a complete substrate. Below the substrate you have the metal, which is ground. Then you have the dielectric. Okay. So this is the dielectric, and on the top of that you make whatever line you want to make. So that line, then the dielectric and the ground will make the microstrip transmission. To fabricate this transmission line is much easier. So you have substrate, you simply etch out the things wherever you want. But this one, obviously, this has one concept which is like all the transmission line they have a transverse electric mode, like the transmission that EM mode, where the electric field is going starting from one end and they are terminating directly to the ground as an antenna. But here at edges, if you see here, see this is my conductor, middle one. Below this, the electric field line will go to this perpendicularly. But at the edges from here and this, the lines will go and they will go like they will make a shape. So this is not exactly 90 degrees, it's not PEM mode. So it is the amalgamation of two modes, which is like PEM heavy or nahi PEM. So that's why it is called quasi-PEM. It's a very classical phenomena and it is very renowned, but this transmission line are the workhorse of any PCB circuit design in RF microwave. Later on, when we see the slotted or the suspended transmission line, where you will suspend the transmission line in between, they are really hard to fabricate. So when you say any design, you see this point in very critical manner. Design karna aasan. Anybody will do the design, but design for manufacturability has to be seen. क्या वो design मेरा manufacture होगा या नहीं होगा? How difficult it is. यदि वो design manufacture नहीं हो सकता तो वो बेकार है. So one has to see from that point of view. So this is what is that I was saying, strip line. So it is also good, but obviously this has a very low tunability and it is very difficult to fabricate. Because in between you are having the transmission line. So these are different kind of transmission line, which is like you make a slot in between, and the last one, which is the CPW, where you have a three transmission line. What do you mean by transmission line? Is it familiar to you? Like you are running some signal on the top of that from one end of this middle conductor, and sidewise two conductors which are acting as like a ground. Earlier what was there? In a microstrip you are having the ground below that. So you are having the downward electric field. In the CPW, when we say, then the electric field line will go like, they will start from the middle conductor and they will terminate to the sidewise conductor. So here you have a signal and then you have two metal lines which are actually behaving as like a ground. Now you will say why this CPW and why this microstrip line. You should understand this thing because when we say I have designed my circuit, now I want to translate this IC into some system where this had to be RF connectorized. So if you see these three things like CPW, then microstrip, and the third thing is the coaxial. They are the highly used mode of the transmission. CPW mode is very useful when we say I have fabricated the devices and now I want to make it right now. I am not cutting my device. I have not designed anything. I want to do that is what is called the on wafer fabrication. So in that case, what you will do, obviously you will have the probe tip that I showed in the starting the diagram, that the probe tip which will, one tip which is actually the signal tip will lie on this signal line and the two pin which are actually the ground line, they will lie on those ground line. And that's what we say the GSG, which is ground, signal, ground. So now you can understand that why this CPW line is made. Sometimes when we say the why microstrip line is made, microstrip is, so CPW में disadvantage क्या है? When I will run the ground line throughout my signal, it will acquire large area. यदि ऐसा करना हो, at a very high frequency this is requirement, but up to 40 gigahertz or so we can omit this thing and we can simply use the transmission line in a very first way. But for the on-wafer characterization, we have to make CPW probe. So we make in that measurement area only the CPW. Rest everywhere it is only the that microstrip transmission. So see, these are the beauty of a design, how and where to use all those systems. And then when you are done with the design, you have cut the circuit, you have diced it, then you want to translate this thing to the coaxial connector. So you will put that coaxial connector probe to the transmission line pin and then use solder. So that is what is called the transition from a microstrip line to the coaxial connector. So it is nothing like everything will be so easy. So this translation or the transformation, they will occur also some kind of a losses. So that translation from microstrip line to the coaxial line, those losses have to be taken into account in before of the design. So this is what the transmission line. So this is what I have told you, that while doing the design of the transmission line, these are the things which you have to see. So physical kind of thing, what you have to see, the dielectric epsilon r, the thickness of the substrate, and you know what we are saying, the copper, which is the transmission line copper, which is actually the signal line. So the thickness of that copper also plays a role. How it plays a role? Like when we say the copper clad thickness will tell you how much power it can handle. Although, see, now is a contradiction. So you can ask that we have told that the current is flowing only, the AC current is flowing through the surface only, then why the copper clad thickness is coming into picture? When we say, then when we are going to design amplifier or something, obviously the first thing which will come the DC current, which will flow through those paths. So to handle those DC currents, the thickness of that copper clad will come into picture. After RF, there is nothing like, okay, you can have a smaller thickness, but when you are having the DC current in the path, you have to have a sustainable thickness of that conductor which can handle that much of power. So these are the design parameters, and based on that you have to select the substrate. Okay? And
normally, how much thickness is normally kept for this substrate?
Normally thickness,
0.25
normally it comes like, see, again it comes like copper, it is like 70 micron or 35 micron or 70 micron. So when we say very low thickness I want, it's like 17 or even below that. Half on you say that. So why it is so thick, so is less thickness? Because this much thickness is the skin depth, little bit higher than the skin thickness of the copper. Okay. So and then the one important parameter which comes for the transmission line is the loss tangent. What it says, because every material has its the electric field will go down after some time. So distance, so that is what it defines from the loss tangent of that material. So this also defined, it tells that nowadays like a very low loss tangent materials are available like 0.0001. So that will give a very low loss for the transmission.
Sir, in some CPW line, I have seen the ground plane also is there. So what is the purpose of that?
Yeah. See, in microwave domain, what you want? You want the confinement of your circuit. So obviously, in what I told you in the wafer, in our wafer also, like we have a complete ground plane below of that wafer, and wherever you want to have the measurement on top of that, you define the CPW. So it's not like that only from whenever I am running from here, like on the top, only the CPW is required. Below ground also provide you the better confinement of your signal. So at a very high frequency where the CPW are run, like CPW are used, they have a below that below ground the substrate also they have a confinement ground. That will give you the better confinement of the signal.
Suppose for the antenna design, so which one is better? Normal CPW or ground CPW?
Ground, obviously with the ground.
That is the better.
Yeah. And it depends obviously how you are designing the antenna, which antenna you are designing. So that is what is the whole domain you are having. So now we will move on to the basic of the S parameter. So this is what why S parameter, you know. Let me know the time also, how much time I am left, so that because this will go on. So you know that the circuit, why this is coming into picture. A good picturization, let me tell you, I can, yeah. So it is like, ये वही वाली बात है कि जब तक हम when we work on a lower frequency, so this is what is like a big trap is there. For that big trap where the wavelength is very high. So big trap is depicting here the wavelength of your design. So when I say I am designing in a kilohertz or something, then my wavelength is like a meters or something. So for that meter kind of wavelength, my component are like a small tiny object. So होता ना बड़ा आदमी होता है उसको होता है छोटा है छोटा मतलब कोई फर्क नहीं पड़ता. Okay? We don't bother about the size of the component when we are designing at a lower frequency. So see, so this bump for this lower frequency, lower wavelength, like a higher wavelength in a lower frequency region is nothing, is peanuts. He does not bother about that what are the component size, what is the circuit size and all. When I am working in a gigahertz range where my wavelength has become comparable to my component size. So now this track has reduced to the, see, this small tiny car. So now for this car, this component size is becoming comparable. So now see the signal which is traveling through this component in a high frequency domain will feel the spatial variation. See, you understand this thing? For this trap, this bump, like for this wavelength, this bump is nothing. It will simply cross. For this, my spatial variation is nothing, is zero. But for this high frequency, the spatial variation means when it will cross this bump, everywhere it will feel different. That is where comes the picture. You cannot measure the high frequency signal by simply at point. At each spatial location, the impedance or what we say the parameters will go on change. So that is what is called the approach, distribute approach. When we say the DC or something, we say the lump component approach. I take my resistor as a lump component and I say this is my resistor 100. But you can never say in a high frequency domain where you make some component like a 100 ohm or something, you can never say that I have measured here 100 ohm, it is 100 ohm. No. At each and every point where you will measure, it will have some different impedance. So that is what is called the distribute approach, and that is what is used in the design also. Okay? So this is what is the concept. See, these concepts gives you the basic understanding why and how these things are used. So whether it's a bump or a mountain, it depends on the person who is perceiving. Okay? So why S parameter? S parameters are used because you cannot get, normally what we do, we do the, let me take it. So when we do the two-port parameter, how we do? We simply say that you measure either the V20 or I20 or you make an open circuit or a short circuit. But here in the S parameter, when we say, it is not like why S parameters are coming into it. Then when we want to measure the high frequency powers and signal, we cannot make ideal open or ideal short. So in that condition, what is defined as like a we measure the incident and reflected powers at each port, and then take the ratio of those incident and reflected powers, and those are called the S parameters. मतलब S parameter से ऐसा घबराना नहीं है. S parameter is very simple in that term. They are normalized wave power, which is called A1, A2, V1, V2. So it's a very, so if you see here, this is that is what is the analogy here. So this lamps, and we have read all this, that when any media at any media, when the signal is incident on that, part of the signal is transmitted and part of the signal is being reflected. How much is reflected and how much is transmitted, that is told by the S parameter in the form of S parameter, and that is also linked with the impedance. Again I am telling you, it is all like these things are interlinked. So what is happening, you have seen in the, like when we read in the 7th and 8th class, this media is there, water is there. So when light is coming, then light tends to bend. What is that? That is also same thing, because here it is the air, here it is the water. Both of them are having different impedance. There we say it's a refractive index, here we are saying it's a impedance. So the analogy is same, the working principle is same, only thing, the way of representation has been made bit different. So here it is in terms of the power ratio. So if you see, so this is now more explained, like one part is the reflection part, which tells the reflection, and another part is called the transmission, which is called the transmission part. So how much power is being transmitted with respect to the incident power is called the forward transmission. So let me tell you the 4 ports in a very physical manner, otherwise you will lose the interest, or you say the connection. Port 1 is there and port 2 is there. I am feeding some power at port 1. I want that this whatever power I am feeding, it should reach to port 2. That is what is my target. But due to the mismatch or the impedance difference, this will not happen. So let me say I have sent 100% power at this end, and due to the mismatch, 10% power is going back due to the reflection. So how much power will go? The 90%. That is what I am saying, the transmission, forward transmission which is occurring is 0.9. So what is my H21? In that case, how much power is reaching at port 2 with reference to port? That transmitted divided by the incident. And similarly, how much power is being reflected with reference to the incident? So that will tells us the reflection coefficient at port 1. And the similar thing will be happening at the port 2 also. Whatever power is coming at port 2 will be reflected at port 2. So that is where in S parameter domain we have 4 parameters in 2 port parameter, which is reflection coefficients at 1,1 and 2,2, and the transmission coefficient is S21 and S1. So if you know these 4 points, it is much easier to understand and know about the parameters when we do the design of a power amplifier or a low noise amplifier, that you will learn in a subsequent lectures what are all those parameters and how to harness those parameters while designing. Okay? So this is again, so here again obviously when we are calculating the reflection parameter and the transmission parameter, we have here we do not do the open and short. Let me tell you. I think we are losing interest. So we can, I think we can concentrate on this thing, because later on stage all those things will be linked to this. Okay, so let us go this way, that the way 4 parameters which were measured in a two-port low frequency domain by making either open or short. Here, what we do? We make the reflection, try to make the reflection zero. So how someone can make reflection zero?
That's it.
If I make that code fully meshed, then I say my reflections are zero. So that is where the concept comes. If I put it 50 ohm termination at that code, because I am measuring all those parameters, that is what I am saying in a 50 ohm environment. And that is where this is a very important concept. When I say I am defining my S parameters, then I really have to say in which environment I have measured. Someone can say my S parameter of this system is, let's say, 1 plus G. Other person can say the S parameter of this system S11 is 2 plus G. And both are correct. How? Both are correct. Because the one underlying condition you haven't asked him. I have measured this S parameter in 50 ohm environment. The other person can say I have measured the S parameter in 100 ohm environment. And this is very important concept. Like everybody confused with this. So you should be very fine saying that these S parameters are in normalized this impedance environment. Okay? So normally we measure this power in this when we say define these things, and S parameters are always told that I have measured this in this 50 ohm or anything any Z naught. These are the generalized S parameters are also measured. Then someone says I have measured S parameter in Z naught environment, and this Z naught can be anything.
So one question I want to ask you. One transmission line we are giving to the network.
Yeah.
Power is given to the network high transmission line.
Yeah.
But power is coming from the source. And source is having some impedance. So is it required to match that source impedance with the transmission line impedance?
Yes. That is where the things is. Here the whole game is of this thing that if I am feeding my signal to the transmission line, but at that moment of time you have to see this transmission line is leading, obviously ending somewhere. Obviously, you have to see the complete network. And if I say, see, this is my complete system. You are saying this is my transmission line, and this is my load, whatever extra. So when I am saying I am feeding signal from this end, then I have to see the complete picture of this. It's not only transmission line, the complete kind of thing. I am seeing that. So we have to see the complete impedance, how much it is there.
So that means I have to know that the impedance of the source also.
Source, yeah. So that's why like the source which from where I am feeding, they are normally 50 ohm source. If you see your signal generator or your
What source are 50 ohm source? Normally.
See, this sentence is very critical by saying normally all the sources are which are used in a normal day-to-day life are 50 ohm. But it can be different also. And that's what I am saying, that that's where the concept came in the microwave industry or in the RF domain. Everything is to be designed in some standard domain, like in some standard domain. Okay? So this is all the same thing what I have told you, that the S parameters are in form of the A1 and B1, and A1 and B1 are the normalized power. Okay? So this I have already told you with reference whether it's a S12 or S21, the port number will signify. When I say S21, I am saying the first reference to is the where the power is being measured, is going. So when I say S12, the power is coming back to the port 1. Okay? So this terminology should be very clear which one is the port. And from S parameter you define the 3 parameters, which is reflection, the VSWR, and then you define the rho, which are actually they all are linked. Again I am saying, don't go with this mathematics. You simply understand from your angle that when I say that when I am reflecting complete power, when I am reflecting complete signal, then whatever power I was feeding, it is completely reflected. There is no transmission. So this will define the value of the gamma. When I say my gamma, how much it is the gamma, then it will say either it is a 0 or it's a 1. And that will define whether it's a complete reflection or there is no reflection. Okay? So gamma 0, when say there is no reflection, which will define in terms of dV, define the minus infinity. Log 0 is minus infinity. Similarly for the VSWR also, it will define from 1 to infinity. So these are the way how we can look all those parameters, all 3 parameters. So this is VSWR. So now we say, when I say one important parameter I want to tell you, when I say I have designed some system and it is having 2 parameters. One is the return loss. What do you mean by return loss of that system? That the port 1, if I say port 1, ideally what should be the return loss? It should be minus infinity. I want ideal condition. But in ideal, obviously, no one can get it. So, in normal case system design, we say, okay, 8%, 10%, up to 10% तक यदि reflection हो रहा है, it is sustainable. So normally minus 10 dB, or if it is good, obviously minus 20 dB will be even 1% reflection. So better, like more and more negative side, it will be better. But in practical design, we normally say, अगर 10% तक reflection चल रहा है, minus 10 dB it is coming, it is good for me. So then comes the next part is the Smith chart. I will just go through a bit because I think time is running out. So Smith chart को थोड़ा सा समझना, मतलब थोड़ा easy वे में समझो इसे. हमने अभी तक क्या पढ़ा है? Rectangular plot we know. You know x plus yj. We normally say that 3 plus jx in impedance domain. So in microwave domain में ना हर चीज क्या है ना limits तक पहुंच जाती है, infinity and all. So what the person, this person P.J. Smith, what he thought, why can't I, how can I represent those infinite impedances at those rectangular plane by bringing those infinite and bring both hands and close, make as a loop, like a circular loop. So if you see over here, this is plus infinity side and this is minus infinity side, and then if you try to merge them, go slowly, if you see here, and then you make them as a circle. That is how the Smith chart came into picture, like transformation from rectangular plot to a circular. And why this is useful? Because this is actually a normalized plot, which is chart, which is actually gives a better understanding of impedances. So the derivation and the best part of this is, if you see over here, I will tell you in a very simple manner that the middle line obviously is what? Is the resistive line. There also we have seen, and the upper half of that is inductive, and the lower half is the capacitive. So what all those circles are telling, you understand that. Then the life becomes easy. That the circles, if you take any circle, if you see here, if you take any circle, like let's say A, this circle represents a constant R, because when you go on this, the resistance will remain same. Only thing what it will move is the capacitor or the inductance. So if you will move on the upper side, the inductance will go on increasing. If you will go on the reverse side, then the capacitance will go on increasing. And amalgamation of these both representation gives, like, let me tell you this thing that Smith chart is actually in 2 modes. One is you are seeing over here is the impedance Smith chart. The mirror image of the same is called the admittance chart, where the Y. So the first one shows the Z and the reverse side shows the Y. And if you will mix both of them, then it's called the combined Smith chart. So this gives to the designer a flexibility to move on to the impedances. So you understand only this one graph, that some designer want to match, that's what I told, like 25 to 100 ohm. So how it can be designed? So what he will do, he will start from A, he will move on one circle. See, all circles are there. There's so many circles are there. Wherever you are there, you simply move on to the circle. Wherever the circle is moving. So see A, and you will see which circle is suitable to me. So this is moving to this circle and it is reaching to the C, and you see which circle can be made which can come down to D. So by adding two components, one is the inductance and another one is the capacitance, I can go from A to D. So that is what is the beauty of the Smith chart, which tell you to transform the impedance from one end to the other end. So this is what is the Smith chart in a nutshell. Like it tell us and the other end, one more thing, at the end of the Smith chart is one is the short and another is the open, from where you are starting the impedances. And this is what same thing it is telling. Like if I want to increase the L, I will move on to the clockwise side. If you want to decrease the series, and if you want to in the shunt side also. So this gives the four combination of the matching network. That is what is the matching network. So that's why I was saying that the impedances, two different impedances, and then you want to match those impedances. It is done by the help of Smith chart with the understanding of the S parameter, which will give you the better reflection coefficient and the better transmission. So this is nothing but I told before also that you define matching network at each and every point. It is like whether input side or the output side. So this is a very famous quote, like when we say like Smith chart is nothing but like somebody is driving a car in a not very straight lines, but it is a circular lines where by moving the car you are landing up to the desired destination. So Smith chart is that tool. Okay, so this is what again the representation of the same view, that how you can go from one point to another point by making of the series or shunt L or C combinations. Okay, this is what example. I think this will be done thoroughly when you will do the design of a amplifier. So now most of the things I have told, but so this is what I told you, that MIC versus MMIC, like breadboard to the PCB design to the MMIC design. So see, if you see the MIC where you have discrete component and then you translate those things in a single code, which is the MMIC. Okay, so this is what is the thing in the very first slide. Also I explained this thing, that you have the working boards is the device, and the device are used to design the circuit, and then they are placed in a tile, and the tile is repeated over the wafer. So this is the four component of that. So this is what is the complete development cycle, which is like you do the device design, then you do the processing, and then you do the characterization of that, and then you do the modeling of that, and then you use those models to do the circuit design. So this is what is the, I think I will require 10 more minutes, or it is running out. Okay. So I want to give you a little bit, I will rush through this, I will not go into the equations, but you should get the feel. See, ये ना एक ब्रिज है, मतलब you say डिवाइस बनाने वाले ने डिवाइस बना दी, okay, he has made the device. Now designer जो सर्किट डिजाइन करने वाला है, he has to design the circuit. So how he will do? Obviously he will require the data from the device designer. अब डिवाइस डिजाइनर कैसे डेटा दे सकता है? How he can? Either you do the characterization of the device and give the data to the designer as a measurement data, and then he do the design. But this is very cumbersome way of doing. Like every time you will have the design measurement data and then you do the design. This is not the way how a technology is developed. So what should be done? Each component, whether it's a resistor, whether it's a capacitor, inductor, or any component or a device, they should be characterized and they should be translated into an equivalent circuit model. What do you mean by equivalent circuit model? Like you are translating the physical device performance in the form of some network, electrical network, made up of a RLC again, or any voltage source, current source, which can be run on a simulation tool and which actually mimic the performance of the device. Are you getting my point? Measurement data is there, it's okay, you can use the data, you can do the design. But that is a crude way of doing it. It will not give you the flexibility of maneuvering, tuning, or playing with the parameters, or you can say the analysis also you can't do in beforehand. But with the model, which is having, so this is what is the model where we see the equivalent model, this one. So this is the device, and I want to translate this device in the form of RLC component. Obviously, it is not a random kind of thing. You will translate this device with a physical explanation that why I am having this R, why I am having this capacitor, the current is flowing, so I will have the current source. So this is what is a translation of a physical reality into the component. So let me tell you the example in terms of inductor. So how we make inductor? You make inductor by some transmitted lines. When we say this is a physical inductor, how you will model this? So this will, what it will have? It will have its own inductance. Then this transmission line, which are actually these lines, metal line, they will have, between those, they will have stray capacitor. See, everything is like a physics from the physics model. So to take into those account of the physics, the capacitance between these two, you will add one capacitor, which is stray capacitor. And also this transmission line, which is running on the substrate, will also make a capacitor. See, the below is the ground, metal, top of the metal, and in between the dielectric is there. So this line will also make a capacitor. So to model this actual mimic this inductor will have so many components. So I want to make inductor, obviously 1 nanohenry, 2 nanohenry, but this will have so many components. Okay? So to have a mimic of those components, a modeling person will try to make as good or as equivalent to this physical device. Similarly, when we say that MOSFET or a ham structure, there also what you do? I will show that. See, so this is my MOSFET ham. For each and every component which are like pad, source pad, drain pad, or the gate which is underlying that. So each and every component are actually, all the actions are being replaced by either a capacitor or an inductor or a resistive part, which are lost. So that's how you translate a FAT model into the equivalent circuit. So there is a modeling person, what it does, it takes the measurement and then try to get all those parameters by so many measurements, and that is what is called the extraction process, the modeling of the device, which is a very well defined, but it's a very cumbersome and it's a very tedious job to get all those parameters. Once someone gets those parameters, then say, let's say this is the physical device, this is my model. Now let me do the simulation, whether they are matching or not. So obviously the model accuracy depends how good you can match both physical device to the actual device. Once these devices models are there, all the components are made as a PDK, and then those PDKs are given to the designer in a tool which is like a ADS tool or a cadence tool, where all those components are there. He will simply plug and place on the circuit schematic, and then will. So for the designer, on the front side it is the device, but on the back end of that will be this one. Pardon? Yeah, this is the drain. This is the type of mistake. So gate, drain, and below is the source. So this is the extraction procedure. I will not go because the one who is doing the modeling he does the measurement at cold or the hot bias parameters. From there, it does the extrinsic of each parameter one by one step. So this is the complete process of the modeling that we do. So from there we define those extrinsic parameter as well as the intrinsic parameter. So this is the full process of the modeling. I will not go here. This is like step by step removing all the parameters. So this is how we get the complete model parameter of our fat device, and then we check how good my model is. So I am seeing the measured data and the model data. So up to what frequency I am getting. So this is like 1 to 30 gigahertz we have seen. So this is a perfect match with a very good accuracy. So this is what is the complete algorithm that we make. So this is what is a point model, but in reality, when we do the power amplifier, the nonlinear simulations, for nonlinear simulation, the high power devices, we have the nonlinear model. So that is what is having more number of equations, which defines the current in the form of more and more complex level. Someone says the quadratic equation and the tertiary. So these are the models for those MOSFET and HAM devices. So over the period of time, so many devices which are actually the FAT devices and the HAM devices, the models have been developed with a cubic or quadratic equations of the how good you can match the DC of the devices. So this is the one of the important model, which is the Angelov model, which is nowadays are used in the nonlinear domain for the characterization or the modeling of the GAN devices. So this tells us the better accuracy in terms of high power applications, and this model have been integrated into nowadays in all the software, the EDA tools. So this is what I was trying to say. This is the like a design to market, like how good you can come into the market with the design. It depends how good model you are having. So this is what is the PDK, which is designed and it's given to the user. So this is the interface between the designer and the foundry with the PDK, with the help of the PDK, and they do the design. And this is what I told in the starting also. I have given you the basic concept, how the circuits are designed, and to make a complete system starting from the device, bare device, leading to the TR modules, and then finally leading to the SR radars. So this is, so here I would like to acknowledge my director from SSPL and the complete division with whom I am working, and to the fabrication team at Hyderabad. So thank you. Thanks for patience listening.
A round of applause, please, for Dr. Umakant Goyal, who has just enriched us with his invaluable insights on the basics of RF and microwave. Thank you, sir, for sharing your wealth of knowledge and expertise. As a token of our appreciation, we would now like to invite Mr. Ajay sir, to please present a memento to Dr. Umakant Goyal. This small gesture is a symbol of our gratitude for his enlightening session and the time he has dedicated to enhancing our understanding of RF and microwave design. Sir, please. It is indeed a pleasure to stand before you today as a representative of ECE department, extending a warm welcome to all of you gathered here. We have all come together for a significant event, the 6-day Atal-sponsored FDP on semiconductor materials, devices, design and applications. This FDP is not merely a congregation, it is a convergence of minds, a collaboration of academia, research and industry experts, all sharing a common interest in the vast realm of semiconductor materials. विद्या मन का आईना खोले अंतर द्वार करे विनत विद्या सदा दे विवेक उजियार. A warm and esteemed welcome to each one of you. Today, we are truly honored to be in the presence of the distinguished dignitaries who have graced us with their presence. Amongst us are visionaries and leaders who have played instrumental roles in shaping the path of our institution and guiding us towards excellence. We are privileged to have with us today our esteemed chief guest, Dr. Subodh Jindal sir, whose presence adds immense value to this gathering. Dr. Jindal's contributions and expertise have significantly enriched the fields we delve into, and we are honored to welcome him to our institution. Big round of applause.